Welcome back to this series where I describe how we can model dynamical systems using lenses. In today's video, I'll introduce a new composition operation, namely the parallel product, which allows us to put two systems in parallel. To follow this video, you'll only need to know what a lens is, so if you haven't seen the first video in this series, I suggest watching it now. You can find a playlist containing all the videos in the series by clicking on the info thing that should appear right now. Also, if you enjoyed this video, please consider liking it so that other people can find it more easily. Recall from the first video that we were able to use lenses to implement Moore machines, which are ways of expressing open dynamical systems. So in this context, we drew a system S as this type of box, which had some input wires, which I'll label with IS, and had some output wires, which are labeled with OS. And we thought of such a system as taking an input in IS, then somehow transforming it into an output in OS. The way this worked behind the scenes was that this type of system was actually a specific kind of lens, namely of the following type. So it was a lens that had domain, this pair of sets S and S, and as codomain it had the input set over the output set. Then its pass-back map was called update, and here I'll subscript it with S, so it's up S, and it had an output map out S. So this is the notation we had for this lens. And in case you don't remember, so up S is a function that goes from S cross IS to S. So it takes the current state of the system and some input and produces the new state. That's why it's an update. And out S is a function that takes a state and uses it to produce an output. Hence, we can think of such a system as running dynamically through time as follows. At a specific time, this system will have a state, and we feed it some input, and we use the update function here to produce a new state based on that input and the past state. And then that new state will produce an output using the output function. Therefore, by sequentially applying first up S to this input and the current state, and then applying out S to the new state that the update produces, we get a way of converting an input into the system into an output. Okay, so that was a brief recap of how we implemented systems in terms of lenses, and recall also that the system is a special type of lens where these two sets here are the same. All right, so now our goal for this video is to be able to put two such systems in parallel. So the picture for this is that next to S, we also have a system T, which has states T and takes inputs IT and produces outputs OT. Similar to above, the data for such a system is given by two functions, up T and out T. And the signature of this lens is TT, and it goes to IT over OT. So it's exactly the same thing as with S, just we've replaced every subscript S with a T. So I'll just write out the signatures of these update functions quickly so that we can have them for later reference. So up T goes from T cross IT to T, and out T goes from T to OT. All right, now let's think about what it means to have these two systems running in parallel. So the way I've drawn it is I've drawn S above T, and the conceptual move we're making here is now that we're considering this entire thing, so S and T together, as one big system. So what I'm doing here is actually I'm drawing a big box around both of these systems, and I'm thinking of everything in this box as a system where S and T are running in parallel, which I'll denote S tensor symbol T. Somehow in our drawing, this doesn't really make a difference because we're already thinking of S and T being in parallel if we draw them in this way, but in the way we're going to implement them in lenses, it makes a difference, and we have to define what we mean by putting these two lenses here, which represent the corresponding systems, in parallel to get a new lens, which will just be a single object. Now notice in this picture, we've gone from systems having a single input and output wire, so S and T each have a single input and output wire. We've gone to a new system, so this big yellow box here, which now has two input wires and 2 output wires. So the inputs into this system S tensor T are on the one hand inputs in IS, and also at the same time it's taking inputs in IT. Similarly, it's also outputting on 2 wires. So we have this output wire OS coming out of this system, and also in parallel an output wire OT. Finally, if we look inside the system, we also see that there's sort of 2 boxes happening in parallel inside the system. So now we have to think about how to make sense of all of these things happening in parallel in terms of our objects. So the first thing we're going to think about is what types of states S tensor T will have. If we look at the picture, we see that the state of S tensor T consists of 2 states, namely a state of S and also a state of T. And moreover, these 2 states don't have any interaction with each other, so we can get any possible combinations of these states in S and states in T. So therefore, the states of S tensor T are actually just states in S cross T, where this is the Cartesian product of sets S and T, which represent the states in S and the states in T respectively. And the fact that these 2 systems don't interact in any way is represented by the fact that we're not imposing any constraints on this Cartesian product. Okay, and now let's look at what inputs S tensor T takes. So we see from the picture and the wires going into the system that we have these 2 wires, namely IS and IT. And in order for S tensor T to take an input, it needs to take an input both from IS and also from IT. So the input from IS is routed to this inner system S, and the input from IT is routed to the inner system T. Therefore, one input of this parallel system, S tensor T, consists of a pair of inputs, one in IS and one in IT. And again, we don't have any restrictions on these pairs of inputs, so the input set to S tensor T will be the entire Cartesian product IS times IT. Okay, so at this point the pattern should become apparent. What are the outputs to our system S tensor T? Well, it's just going to be the Cartesian product OS times OT, because this system here has 2 outgoing wires, OS and OT, and well, on the first wire we get an element of OS, and on the second wire an element of OT. So whenever this system outputs something, it's a pair of outputs, one in OS and one in OT. Okay, so we've now successfully specified some of the data for the system. In particular, we have enough to write down the signature. So the signature for S tensor T will be as follows. We have the set of states, S cross T, and this goes to a set of inputs, which is going to be IS times IT, and it has a set of outputs, OS times OT. Now, to finish specifying the system, we need to give update and output functions. So we need to find what the update function of S in parallel with T is, and also what the output function of S in parallel with T is. Let me move that up there so that I have a bit more space. And now let's think about what the update and output functions of this system need to be. So perhaps the easier case is the output function, because it has a less complicated signature. So the output function of S tensor T is a function that needs to go from the set of states down here to the set of outputs here. So it's a function going from S times T to OS times OT. Okay, so what can we reasonably do? Well, an element of S times T is a pair, small s, small t, and we need to map this to some pair where the first element is in OS and the second element is in OT. Now let's see what type of data we have given. Well, to map the element small s, we can use the output function we have given for the system S, because this maps an element in S to OS. I see I forgot the subscript there. And similarly, to map the element t, we can use the function out t, because this is a function going from t to OT. This also makes sense if you think about this picture. If we have a state small s in S and a state small t in T, how are we going to get an output? Well, The only thing we can really do is map this S to an output using our output function for the system S, and simultaneously map T to an output using the output function for the system T. Therefore, the definition we have to give for this function is as follows. A pair small s small t has to be mapped to out s of s, comma, out t of t. Okay, so that's what our output function for S tensor t is going to be. Next, let's look at the update function for S tensor t. Again, this will just sort of be putting the two functions we have in parallel, but it's a bit more complicated because there are more sets involved. The update function for our new system has to be a function that takes a state in our system along with an input and produces a new state. So the signature for this function is going to be s times t, because that's the set of states for our new system, times is times it, that's the set of inputs for our new system, and it goes to the set of states, which is s times t. Okay, so what are elements in this domain? Well, we have a pair small s small t as a state. Then we have another pair, which I'll call is it, which are a pair of inputs, one from is and one from it. And we have to map this element to a pair of one state in S and one state in T. So let's look at this picture to see what the natural thing to do would be. So we have a pair of states, small s and small t, and we also have a pair of inputs, is and it. And now if we want to update the state of the system, well, what are we going to do? Well, we're just going to use the update of the system S to convert this state is into a new state, and simultaneously we use the update function of t to convert t and it into a new state t. Therefore, the element of S is going to be the image of our old state, small s, together with the input is under our update function of S. So writing this out, this becomes up s of s is. So that's our new state in S. And then in parallel, we also want to update our state in T. So we apply up t to the element small t and the input it. And that gives us a pair of states, one in S and one in T. Okay, so let's recap. We started with a system S up here and a system T down here, and we put them in parallel as follows. So we drew the picture here, so we had a system S, and we drew it above the system T. And then we conceptually put a big box around this entire thing and think of this as one big system. We translated this intuition into a new system given as a lens down here, which has states s times t, inputs is times it, and outputs os times ot. And if you kind of stare at this notation here, you see that here on the left-hand side we have all the data coming from S, and here on the right-hand side we have all the data coming from T. Now to finish specifying this lens, we have to also say what the update and output functions are. So we saw that the output function takes a pair small s small t and basically just applies out s to s and out t to t at the same time. So in fact, this output function here is nothing but the Cartesian product between out s and out t, because we're just applying both of these functions in parallel. The update function works similarly. Maybe just as an aside, if you also wanted to think of this update function as the product of the respective update functions of s and t, then you would have to first isomorphically map this element here to the element s, is and t, it. And this entire thing could then be mapped to our target element using up s times up t. So the map I'm describing here is a natural isomorphism between this set and the set where the sets in the Cartesian product are rearranged appropriately. Okay, so this basically already tells us what the parallel product of systems is going to be. I'll just recap this formally in the following definition. So the parallel product of two systems, S and T, given as before, is given by the following new system, which I call S tensor T. So it is a system that goes from the domain here, where we put basically the domains of the two lenses in parallel by taking their Cartesian product, to the codomain, where we basically also put the inputs and outputs of the first system and the inputs and outputs of the second system in parallel using the Cartesian product of sets. And it has the following update and output functions. So the update function is as we had before. It takes a pair of states, one in S and one in T, and a pair of inputs, one in S and one in T, and it applies the update function of S to the corresponding state in S and input of S, and then also in the same time it applies the update function of T to the corresponding state in T and the input of T. The output function also works in a similar way. So we have a pair of states, one in S and one in T, and this is mapped to a pair of outputs by applying the output function of S to the state in S and the output function of T to the state in T. Now, I've just given you the parallel product for systems, so recall that systems are lenses of a specific type where the two sets in the domain are the same. We can now easily generalize this idea of a parallel product also to lenses, where these two sets are not necessarily the same. More generally, the parallel product of lenses can be defined as follows. So if we're given a lens F, which goes from A minus A plus to B minus B plus, and a lens G, which goes from C minus C plus to D minus D plus, then we can again form the parallel product in exactly the same way we did for systems. So this will be denoted F tensor G. So we put the domain of the first lens in parallel with the domain of the second lens by taking Cartesian products. So you can see down here that the inputs of the domain are basically A minus times C minus, so that's the Cartesian product of this set here and this set here. And the bottom part of the domain are the Cartesian product of A plus and C plus. So again, if you think about these things in terms of columns, we're just taking the domain of F and sort of taking the Cartesian product with the domain of G. And exactly the same thing is happening in the codomains. So here we have B minus B plus as in F, and we're taking the Cartesian product with the codomain D minus D plus of G. And now the definitions for the pass-back and pass-forward maps of this new lens F tensor G are completely analogous to what we did for systems. So for the pass-forward map H, we're basically just taking the product of the pass-forward maps F and G. So an element small a plus, small c plus in this set, capital A plus times capital C plus, is mapped to f of a plus, because that's what we can do with an element small a plus, and g of c plus, that's what we can do with an element small c plus. Now the pass-back map again looks a bit more complicated. So H sharp has to be a map that goes from a plus times c plus times b minus times d minus to a minus times c minus. So an element in the domain of this function looks like this. So it's a pair of pairs, and the first pair contains an element small a plus, comma, small c plus, and the second pair contains an element small b minus, comma, d minus. And well, the way I've color-coded it to indicate where these elements are coming from, so the blue elements are coming from things in F, and the red elements are coming from things in G. Well, if we have an element small a plus, small b minus, then we can apply the pass-back map in F, because this takes an element small a plus and small b minus and maps it to an element in capital A minus. So that's what we're doing here. In the same way, we're taking these elements that come from the data of G, and we're mapping it to an element in D minus by applying the pass-back map G sharp to these elements. And this then gives us a pair of elements, one in A minus and one in C minus. If you want, you can also think of this construction in terms of a picture. So in our notation from the previous videos, we thought of a lens as converting B minus inputs and B minus outputs to A minus inputs and A minus outputs. So the way this was drawn was as follows. We had here B minus B plus, and then the inside we had A minus A plus. And somehow this lens was an interface between these two different types of inputs and outputs. And well, similarly, our lens G can be thought of as an interface between C minus C plus and D minus D plus. Now we again draw a big box around this entire thing, and then we see that the resulting lens here should mediate between A minus times C minus, so that's here, and A plus times C plus, that's down here. And the outer interface should have input type B minus times D minus, that's happening here, and have output type B plus times D plus. So it's exactly analogous to what we did for systems, just, well, these two things here don't have to be the same. All right, so that's all I wanted to say about the parallel product for now. I think the concept of putting these two systems in parallel is simple enough that if you want to come up with some examples, you should be able to do so yourself. Also, I'll be giving a lot of examples in the next video where we'll be using the parallel product together with lens composition to wire systems together in interesting ways.